And away we go. So what we'll finish up with is our redox reactions with our alkenes and alkynes. So within this, what we're looking at is our reduction reagents. We've got a set of 4. The top 2 will do pretty much anything you want. They'll react with alkenes, alkynes, pretty much any pi bond out there, they're going to go through and reduce it entirely. The bottom 2 are exclusive to our alkynes, and they do some kind of interesting stuff when it comes with our alkynes. And the reason that they do interesting things actually has to do with the fact of their structure. So when we look at an alkyne, if we go through and reduce this just once, so one reduction, and sometimes you'll see it written like this with a hydrogen in brackets over the arrow, so we aren't specifying what reagent, we end up with an alkene. And the issue with that alkene is that we have 2 possible ways in which it can form. We can end up with the cis isomer or the trans isomer for our products. Trans is more stable, but remember, in determining how your products form, it's all about the mechanism. When we go back and take a look at the 2 reagents that we're concerned about here, we have H2 and Lindlar's catalyst, which is a metal catalyst, just like the palladium and platinum above it. The issue with the metal catalyst is that the pi bond interacts directly with the metal surface, and it is now physically bound there. This prevents any kind of free rotation, and you end up getting locked in the cis conformation. If, however, we go through a slightly different mechanism to make the product, then we can potentially get a trans product. That reagent ends up being sodium metal and ammonia. When you go through and use that reagent, we end up making a radical. That radical species, whoops, let's draw that a little bit better. Our radical, there we go, because we only have a single electron, that single electron is effectively existing in a p orbital, so it can oscillate back and forth, which is ultimately then also going to shuttle this R group back and forth until we get rid of the radical. So what's going to happen is that R group will sit in its most stable conformation, or switch to that most stable conformation, and exist in that state for a little bit longer, perhaps, than the other conformation. And it is at that point that the radical will react and pick up another hydrogen, and once that other hydrogen has been put in place, we can now no longer oscillate back and forth with that R group. And we're now locked in that trans conformation. So what you'll need to remember is that if you want a cis double bond, you need to use Lindlar's catalyst. If you want a trans double bond, you need to use sodium metal in the presence of ammonia. Okay, so that's ultimately the big differentiation. If you go through and look at your textbook, the textbook gives you at least a shortened version of the radical mechanism for the sodium metal that might help you kind of grasp it, but what we just discussed here is really all you need. You just need to know that end result. Because the sodium metal goes through a radical, you end up with the trans conformation. Lindlar's catalyst is a platinum catalyst. The alkyne must sit on the surface that forces the cis addition of hydrogen. One last thing I want to throw in there, because you might potentially see this show up, is that we have sodium metal. Whoops. Come on. We have our sodium metal in the presence of ammonia. And if you think back kind of hard, you might remember that we do have another reagent. That other reagent with alkynes was sodium amide. These are two drastically different reagents. Please be careful if you see these. So your sodium metal, you're looking at reduction. Okay? Whereas if we look at sodium amide, this ends up being a base. Okay? So in the presence of the base, we end up with our nucleophile, our nucleophilic, acetylide ion, which was our triple bond with a negative charge on it. In the case of the reduction, we would end up with our double bond and whatever our group was. Okay. One point to note here is that you may look at this and say, well, why aren't you showing that as a trans double bond with the reduction? In this case, the starting material that I'm picking to use is, whoops, that was horribly drawn, let me try that again, is propylide, or, propine. Okay, and the reason why is because I wanted to show this acetylide issue. When you form the acetylide, we need to have an acidic hydrogen to react with the base. If we'd started with, instead of propine, with maybe butane, 2-butane, that case, there's not going to be a reaction with the sodium amide. We'd get no reaction over here. Why? There's no hydrogen. You have to have a hydrogen attached to the sp carbon. And if we go through and specify in here, we've got a CH3 at the end, CH3 at the other end, and then our carbons in the middle of the structure with no hydrogens attached, so we can't do a reaction there. Okay? So the base reaction with sodium amide only works with terminal alkynes, when you got the alkyne at the end of the structure, or at the end of a chain. The reduction reaction will work anytime. Okay? So I know those reagents overlap a lot, but they are drastically different things. Red flags that you're looking at sodium and ammonia and not sodium amide. Look for that solid phase symbol to show up. For sure, look for the sodium on its own. Okay, another way that we could have written that out. So let's erase the sodium amide now. Excuse me. You might also see it maybe a sodium /NH3. Okay. What we're trying to show in that situation is that the sodium is separated from the NH3. It is in there as a metal. It is not in there as an ion. Very, very, very different chemistries. And here we can see those end results. The Lindlar's catalyst gives us the cis double bond, and our sodium metal will give us the trans. So here we've got a summary, kind of shows everything that we could work with. I went through and made sure to specify the alkane, or the alkene, and when you go ahead and look at the final product for each of those alkene reactions, you'll notice that the stereochemistry maintains the same. Okay, the R is still trans to the R3'. Okay, that is going to be forced to occur because of this syn addition of hydrogen. Okay, and it's semi-concerted. So what's happening is the hydrogens are coming in on the exact same side. If we're going to look at it in this case, we'd either say our hydrogens were both wedged, okay, coming in directly from the top or directly from the bottom. Because it is an addition reaction, we do end up with the possibility for enantiomers, because our pi bond is made up of p orbitals, which has both a top and a bottom lobe, so watch out for that. If we go through and look at our alkyne, you'll notice that if we go through and use the H2 in palladium or the rainy nickel, which should have an H2 on it, I don't know why it doesn't. If we go through and use those reagents with the alkyne, you will completely add hydrogen to that structure. Please also note that this is not cis. Why is it not cis? It has to do with our hydrogens. There's nothing to really be cis around. Okay. You've added 2 hydrogens to both those positions. They can't be a stereocenter. Okay. You're still going to be doing a syn addition, okay, of the hydrogen atoms, but you probably won't see this cis issue pop up. If we switch over to using Lindlar's catalyst or the sodium metal, we'll see the syn addition in the case of Lindlar's catalyst, and in the case of sodium metal we see the anti-addition, which is going to give us slightly different results. The anti is really going to force and actually, now that I think about it, maybe it's too early in the morning. Let's stick with cis addition, so the result is a cis double bond, which will be a syn addition. And then the sodium metal, I'm not quite sure we can actually call that strictly an anti, but for sure it ends up with the trans product. Okay, so you need to remember that, lock it in your brain, you'll be ready to run. Whoa, okay, good. Now we've got the alkene oxidations. This summarizes everything within this, or within our oxidation reactions. It does look like a lot. What I would try and do, if I were you, is try and break it into individual sections. And that's what I went through and did when I presented this. We'll look first at our mCPBA reactions. Then we'll look next at our permanganate and osmium tetroxide, because we end up forming diols in both of those, and very similar diols. And then we'll look at ozone as a last reagent. Ozone is a really popular reagent within the ACS test, so I do highly recommend that you kind of remember that one, because you can use ozone and then change the second reagent that you're working with and get drastically different results. Same kind of idea with the epoxide, which we'll talk about on the far right. Okay. For each of these, all we're doing is increasing the oxygen bonds. That increase in oxygen bonds is then an oxidation reaction. Also with each of these, the mechanism becomes a little bit less important. The end result is going to become really, really important. The one exception to that is your mCPBA. That mechanism, at least next semester, I will for sure test you on, just because I think it's a neat one. The metal oxidation reactions with the osmium tetroxide, the permanganate, and the ozone, you don't need to know those mechanisms. You're just responsible for understanding how they exactly work. And so we'll address some of the intermediate stages in those reactions, and hopefully that'll help trigger and get you to remember the end result, okay, or at least the stereochemistry of the end result. Shoot, keep double tapping. Let's make sure I didn't go too much further. So with our mCPBA, what that's standing for, I guess I can write that across the top here. It's a massive name, but we've got meta, which is a nomenclature thing that we haven't talked about yet. Meta chloro peroxy benzoic, jeez, it's massive, benzoic acid. Okay. You will undoubtedly see it as mCPBA, because as we've seen already, chemists are lazy. What's happening with this reagent is that we are converting an alkene into an epoxide. So typically the way it's written out is mCPBA on top, and we're just looking at that conversion across to the alkene. What we're going to be concerned about now is the question of, is this a sequential mechanism or a concerted mechanism? And the reason we need to address this is, if it's sequential, what that means is we form one bond of our cycloprop-ish ring, and at that same instant, or at that time that we form that one bond, we no longer have the pi bond, which means we have a sigma bond in between, which means we have free rotation. That free rotation is going to change the orientation of the substituents around it. So let's go through and pick one. So let's say we ended up or started with something along these lines. Okay, an internal alkene, so we've got two R groups. If we went under the sequential method, i.e. we went through steps, we could form the bond, and then we could have the sigma bond rotation, and when we look at our products, we would end up with two possibilities. We'd end up with the possibilities of our R groups being right next to each other, but then we would also have the possibility for our R groups being away from each other because of that sigma bond rotation. And because having them away from each other in theory makes a little bit more sense, we might actually expect to see those as far away from each other as possible. Okay. The other option is we go through a concerted mechanism, and if we start with our alkene as it is, we form both the bonds at the exact same instant, or relatively close to it, and if we form both those bonds, we've locked the structure, or locked our ring structure, and we now can't do any rotation about that bond, which means we only end up with one possible orientation. Okay? And those R groups would have to be on the same side of that ring structure. And so that's really what our epoxide mechanism or our epoxide reaction is looking at. Okay. So before, and I should have done this a little bit earlier, what is an epoxide? An epoxide is just a three-membered ring where one of those atoms is an oxygen atom located within it. They do tend to be fairly reactive because we have a propane or a prop type ring, so we get a lot of angle strain in that, which is going to make it really want to pop open, which is one of the reasons why we end up using it, and nature uses it fairly often as well. And it's because we can then pop it open. But before we pop it open, we need to know how it can form. So that's going to come back to our mechanism. So how do we decide what mechanism is the result? Well, some chemist comes along and says, I think it's sequential, so I'm going to run my reaction to prove it. Okay? And if they're going to do bad science, what they might very well go through and do is say, well, I'm going to prove it's sequential by using this alkene as my starting material. Okay, well, what's going to be the problem with that alkene as a starting material? Well, we'll have the R group on one side, and then we'll have hydrogen on the other. Is there anything to compare that R group to? Nope. So that starting material is a horrible starting material to use because we can't really determine whether it's sequential or concerted. So some other chemist probably comes along, looks at that and says, you're an idiot. We need to fix that. So they come in and adjust, and they say, at very least, we need to have another R group on there. So they add another R group. Okay. So we now have that situation, and we look to see what the products are at the end of this. And what we end up finding is that we end up with the R groups only cis to each other in our final product. Okay? They are right next to each other, there is no difference. That's a bit interesting. That is then going to suggest that we don't get that sigma bond rotation. If our R groups are always cis, then we can't do the rotation, because if the rotation was there, it generates a more stable product. So we would have expected that. Okay? We didn't get that. So he reports that and says, oh, those are my results, those are fantastic. And everybody goes, oh, yeah. So somebody else goes and says, well, okay, what if you instead started with the trans? Okay, because maybe there's something weird about the cis relationship that's actually making it more stable. So let's go through and try it with the trans alkene. Okay, well, what happens now? When we go through with the trans alkene, if we are still expecting this concerted mechanism, what would our product look like? Okay, so where would the R groups be relative to each other? And I'll give you a second here to attempt to draw on with your notes. And that's a long enough second. Well, we can put on the one side, and if we now go through to finish up, what happens on the other side? Oh, look at that, thank goodness. We get something reasonable. Our R group are trans to each other, so we do fully expect to see this. What we're looking at is a concerted mechanism. So someone much more brilliant than myself, because I'm really not all that brilliant, went through and attempted to discover a mechanism for this. And so what they decided was that we do have this very weak oxygen-oxygen bond. Okay, so they said, okay, well, if that bond is weak, and I know my alkene needs to act as a nucleophile, okay, why does it need to act as a nucleophile? I know that's a common question that keeps popping up, that in theory, if you're one of my students, you aren't asking that question. What is in our alkene? We have electrons. Okay, that's what our alkene acts as, which means with those pi electrons, it must act as an electron donor. And since we aren't looking at it reacting with hydrogen in this case, it's got to be a nucleophile. So if we look at our alkene bringing its electron, that pi electron, up to that oxygen, we can now polarize that oxygen-oxygen single bond, and we can have those electrons swing up to our other oxygen. Okay? Well, that forms one side of our pi bond, but not the other, so we've got to be a little bit careful here. You'll also notice that in that top arrow swing, this guy, that I'm moving it to the space between the carbon and the oxygen, which means that carbon has too many electrons. So what happens then? Well, then it says, well, F you, I don't need all those carbons or all those electrons, so it puts that electron density onto the oxygen up here. Well, that oxygen already had a pair of electrons, so it's saying, well, shoot, I've got too many electrons now. So what it does is it swings and picks up a hydrogen. Okay, yeah, this is arrow heaven, isn't it? Well, now the hydrogen goes, well, shoot, now I have way too many electrons. I need to dump off some. Okay, and before we decide to just dump those off willy-nilly, let's think about all the way back to the beginning and what happened to our alkene. Our alkene, okay, ditched its electrons, and we're effectively forming the bond between that carbon and the oxygen. Okay, but what happened to the other carbon? Okay, our other carbon in here just lost electrons, so it's now formally positive. It doesn't want to be positive, so it needs to get electrons. What happens? The electrons in that hydrogen-oxygen bond come down and hook up with that carbon. The net result of this is that we end up forming both our carbon-oxygen bonds of our epoxide at the exact same instant. Okay? And at the same time, the rest of that peroxy structure effectively decomposes or rearranges to generate a carboxylic acid, which is vastly more stable than the peroxy situation, because we no longer have that oxygen-oxygen bond. Okay, so crazy looking mechanism, lots of cool arrows floating through it. I think it's fascinating just because of all the arrows. And just as one more thing, I'll go through and add those arrows in here a little bit nicer so we can see that without too many different colors. So again, we have our pi bond attack our oxygen. We have the electrons in our oxygen-oxygen bond going to form a new pi bond. We have our old pi bond going to our oxygen, We have our oxygen attacking the hydrogen, and then we have the electrons in our hydrogen, and our hydrogen-oxygen bond going back and attacking our carbon. So we got, what was that, 5 arrows all in a single step. Okay, I know previous reactions say, oh no, there's only 2 or 3 arrows at most. The epoxide reaction is pretty cool in that respect. We got 5 different mechanistic arrows happening all at the same time. Neat stuff. So, concerted mechanism, no sequential method. What we're looking at is the stereochemistry maintained in the product. Okay. I didn't address the pictures on the side. Those were an attempt at looking at an alternate view. Those would need to be dashed. Because remember, typically when we go through and draw out our carbon structures, we try and make sure that the carbon chain is all on the same plane. So you might see the epoxide drawn on with a wedge, suggesting that it's coming up. One other issue with this, I only looked at the oxygen or the epoxide forming on the top of our alkene. It could just as easily have occurred from the bottom, because remember, again, we're still starting with that alkene that has a pi bond, which has top orbitals or top lobes and bottom lobes, which means we will still end up with enantiomers in our product. Okay, so watch out for that. Still 2 products. So that is actually the discussion of this slide. We're forming the reaction with alkenes, which means when we do our epoxide, we can form 2 possible products. So I got this pretty nice image showing the epoxide forming either from the top or from the bottom. The result, we get 2 products. Okay. As far as chemists go, or organic chemists, we absolutely hate this, because when we run a reaction, we only want 1 product so we can get a better yield. In this case, if we ran this reaction and we only wanted 1 of these, the best yield we could hope for was a 50% yield, and that's pretty horrible. Okay, and no offense to anybody in lab that gets 50% yields. That's standard. That's okay. But an advanced chemist. So somebody else came along and said, well, that's a load of junk. Let me fix it. So this is where Sharpless came through with a magic reagent, which is referred to as the Sharpless catalyst. And what he noted is that when he used his catalyst and a particular combination of species, that he could force one enantiomer be formed over the other. So we could go from a 50% maximum yield to like 100% maximum yield. And it's kind of an odd process. I have not heard a good explanation on why that necessarily happens yet, other than it just does. So the titanium is there just kind of as a metal catalyst to probably help coordinate things. And what it's really trying to coordinate is this DET molecule. So when we're looking at the Sharpless reagent, or for that matter any kind of chiral catalyst, those catalysts are enantiomerically pure. So we are adding either the plus DET or the minus DET. And if you remember back to the plus and minus, it's how it rotates light. So we have to have these enantiomerically pure species. If we go through and use the plus DET, we end up with one of our enantiomers primarily over the other. And I'm not positive on this, but I think it's the case. You'll end up with the plus enantiomer. If we switched it up, and instead of using our plus chiral reagent, we used the minus, we'd end up with the minus enantiomer with nearly perfect yields. The exact reasoning behind it, don't really know, except that a chiral molecule tends to force other chiral molecules to form. Okay, so chiral molecules get lonely, if you can think of it that way, and they want other chiral molecules just like them to make them feel happy. You could run parallels into life. Okay, so when you, and not that life, like, yeah, beside the point. If we go through and look at amino acids or DNA or sugars, they all have a very particular chiral center within them. And that chiral center is the same for every single one of those. So when we go through and look at amino acids, I think they're I'm blanking on it, but we might be looking at the D amino acids or our L amino acids. The D and the L are in reference to how they rotate light. In all life, we only have one form. It's a 50-50 chance if we look at organic synthesis, but there's only one form in life. Okay? And one reason could be that once we formed one in a slight excess, or once we formed one at all, it forced the following reaction to have that same stereochemistry. Okay? For that to work, we have to have relatively high concentrations of these chiral reagents and all sorts of other fun stuff. So it's an interesting thing as far as life goes. Not super important to mention here, except that Sharpless was pretty cool in showing us this reagent. Why do we want to deal with epoxides? Well, the special deal with our epoxides is that our natural epoxides are precursors to all sorts of active biomolecules. So that's what's shown on the left there. You get a bunch of different structural epoxides. They can go through a sequence of reactions to generate all sorts of other fun materials. Okay, everybody asked me to show something like that, so there you go, fun epoxides. When we move to the lab, like I care about fun epoxides, right? When we move to the lab, what we want to do is now have this reagent react. Well, because of that ring structure, and it really wants to pop open, what we would have to do is supply some reagent to force it to pop open. So if we look at our ring, we have two possible bonds that could break open. Both of those bonds are going to want to swing towards the oxygen because oxygen is more electronegative than the carbon. So we could bring in, well, in either of those cases, depending on which bond breaks open, the oxygen is going to pick up that negative, but then our carbon picks up the positive. Okay. The reason we want to address that, well, is what would we expect our epoxide to react with? Well, it's going to react with something negative. It's going to react with our nucleophile. Okay. So we can bring in a nucleophile to come in and attack those potential positives. The issue we're going to run into is which one does it attack? Okay. Depending on what conditions you're under, we're going to see it attack different ones. And we've talked about this when we looked at the mercury or the mercuronium and when we looked at the bromine reaction, okay, with our alkenes. It's all going to be dependent on the strength of that nucleophile and the strength of our leaving group. If we're running under basic or neutral conditions, our leaving group is pretty horrible. Okay? So if we take the electrons and shift them out there, what we would end up with is this as an intermediate. Whoops. Started to draw hydrogen too early. With our negative, and then we end up with a primary carbocation. And actually I was looking at the leaving group, looking at that O minus. O minus, horrible leaving group. Horrible, horrible, horrible. So we either need to activate it to leave, in which case we need to add an acid. We're under basic conditions, so we can't do that. Or we need to force it to leave. Well, to force it to leave, we need a strong nucleophile. Hence, using a nucleophile in this case with that negative sign next to it. Okay, so if we're looking at forcing it to leave and a strong nucleophile, now we have to decide, well, which of those carbons does that nucleophile attack? Okay, well, if it's a strong nucleophile, it needs to be small and needs to be able to get access to the backside of the bond as quickly and effectively as possible. Well, if it's going to get access quickly and effectively, we're going to want which of those carbons? Carbon number 1 or carbon number 2? Okay, hopefully you're thinking about that. You're thinking, well, nucleophiles need to be small so they can get access in, and then because we want it to act as a nucleophile, it needs to have the most accessible carbon to react with. Well, the most accessible carbon to react with? Carbon number 2, least steric hindrance. So our nucleophile zips in, attacks carbon number 2 because it has less bulky things around it, no carbons, And we can break open that structure, and we end up with, oh great, after a second step, after a second step, after adding hydrogen, we would end up with our alcohol. Okay? So what I'm trying to show with both of these products is the same product is happening in both cases. We're just seeing a slightly different orientation of it depending on where things attacked, okay, or how things ended up attacking. So our nucleophile attacks the least sterically hindered position, generating our O-. So if I want to get kind of nitpicky on this, scratch off that hydrogen, make that negative. Once we have the O-, we can then go through and react it with acid, and we can protonate that position. And we'd end up with our alcohol. What nucleophile can you use? Any nucleophile. You can use all sorts of fun ones. The textbook has picked it pretty much exclusively as the nucleophile hydroxide. And the reason they're picking hydroxide is that we end up with, as a final product, an OH down here as well. Okay, well, what's special about the relationship of those OHs? They are on opposite sides of the structure. We have an anti-addition or a trans result of our OHs. Kind of neat. So, like I said, neat result. So, basic conditions. We're looking at our nucleophile attacking the least sterically hindered site. So let's run through a brief summary, because I don't think I've got a conclusion slide on this. So conclusion for basic conditions, we run what I would call an SN2 kind of type substitution. Our nucleophile attacks least substituted. Okay, kind of an important conclusion for our basic conditions. And why might we say that? Well, what happens if we run under acidic conditions? Well, under acidic conditions, the primary thing we need to be concerned about is that H+. Okay, so we're going to be less concerned about our nucleophile and have to focus on the H+ first, because it's under acidic. We should expect that acid-base reaction to happen first. So with H+ floating around, we need to find something negative. Well, where is there something negative? Good call. We've got the oxygen on our epoxide. So that will pick up a hydrogen. Once it picks up the hydrogen, we'll end up with... come back here. We'll end up with this structure. Okay. In both cases, depending on what we're looking at. Okay. The issue with this is that we now have a very good leaving group, because if the oxygen doesn't want that positive charge, so it can take electrons from one of those carbon bonds and become neutral. So phenomenal leaving group in this case. The other part that we would be concerned about is now looking at our nucleophile. Well, since we're under acidic conditions, we can't have a strong nucleophile, because a strong nucleophile being negatively charged would probably react with the hydrogen ion, and we'd have a weak nucleophile. So we're looking at a weak nucleophile. That means it isn't going to go in and force the leaving group out, because it's not strong enough to do that force reaction. Okay, so what we're going to be looking at in this case is more kind of the SN1 type situation. The nucleophile is going to come in and attack the most positive carbon. Okay, so the one that the oxygen is already trying to take electrons away from. So which carbon is going to be the most stable positive? And we have to go through a stable positive. We don't want to look at an unstable one, because if it's unstable it won't ever form, in which case the nucleophile can't attack. So again, we're down to looking at those two carbons, carbon 1 and carbon 2. Which of those two would generate a more stable carbocation if it actually formed? hopefully you will remember that carbon number 1 is more substituted, and the more substituted carbocation is more stable. So what ends up happening in the case of the acidic condition is our nucleophile comes in and attacks carbon number 1, causes our OH to leave. Okay? And our end result, we still end up with the trans alignment of our OH and our nucleophile. However, the big conclusion coming out of our acidic conditions is that we end up pushing an SN1 type reaction. So not SN in quotes, just SN1, which means that our nucleophile attacks the most substituted. Okay. The result of this is that our nucleophile is just now attached to a different carbon than it was under the basic conditions. The other big conclusion coming out of this is that we still end up with the trans alignment of our nucleophile and OH. Okay, and we really should switch that from being trans, because with this structure we can't get trans. We're really looking at the anti addition. I know everybody loves that term, anti. Okay, but we get the anti addition, and if we had a ring structure, they'd be trans. Okay, and just because I accidentally tapped forward, we do have the summary of everything up there as well. So with our epoxides, for our synthesis, we'll start with an alkene. We'll react it with mCPBA to form the epoxide. We're going to maintain the stereochemistry of our alkene, that cis-trans isomerism around the ring, and that's because it's a concerted mechanism when it occurs. You may see other peroxy acids show up, but mCPBA tends to be the most popular one used as far as reagents go. What a peroxy acid is there's your peroxy, and then to make it an acid we need the carbonyl, and we would need the hydrogen out there. Okay, so that's a peroxy acid functional group, and we don't care what's out here. Okay, and that's the rest of that name, the benzoic and metachloro, all that fun stuff. Once we have the epoxide, we can then react it under two specific conditions, either basic conditions, and we end up putting our nucleophile on our least substituted position, or we run under acidic conditions and we end up putting that nucleophile under our most substituted position. Okay, so it's really coming from the mechanism and looking at each of those intermediates and what's happening in each of those stages, and as a result, what has to happen. Okay, so as far as our oxidation reactions go, this is still kind of nice, if you ask me, because we can look at the mechanism. We have a lot more of an idea on what's happening with it. And I am running out of time, so what I'm going to have to do is break this video into two parts. So I'm going to go ahead and stop with the epoxides, and I'll give you another video posted hopefully next, looking at the metal oxidation reagents, which will be just, here it is, have fun with it. Okay, good luck.